Welcome to qnawire.
Okay, this is a graphing problem, and we're given a plot of position versus time. So this is x in meters, and this is time in seconds. And I'll just roughly sketch out what it looks like. So we have some important points, I think about 20 seconds and 30 seconds, 40 seconds. Looks like this, kind of something like that. And a couple techniques I'm going to use. So we want to find velocity versus time based on this. Okay. This is time, and this is velocity. Now what I'm going to do to figure out the velocity, if we remember that our velocity, we can say is the derivative of position, the time derivative. And so that means that the slope of this graph at any point, if we can approximate it, is going to be the velocity. So we can think of the velocity first as constant all the way through here. Then it starts to increase up to this point, around 30 seconds. And then it starts to decrease until it gets to 0 here, just before 40 seconds. And then it decreases again, and then it slowly starts to increase a bit here. So that's a way to figure out the velocity at any one point in time. And in general, so let's break this into sections. So 0 to 20 seconds, we have a constant slope for the position versus time. So that means we're going to have a constant velocity. And our velocity in that time, I'm just going to estimate. I'll say delta x over delta t for a larger range. It's going to be 20 meters versus, how long does that take? Let's say about 12 seconds. And so that's going to give us 0.6 meters per second. So I'll say here at 0.6, for the first 20 seconds, our velocity is a constant. And then from 20 to 30 seconds, it starts to increase. And at 40 seconds, okay, let's see, 30 seconds, 40 seconds. I need to make this a little longer. At 40 seconds, or just before 40 seconds, this position versus time flattens off. And so we know at that point our velocity is going to be 0 because our position is not changing. So we have to get to 0 here at some point. So from 20 to 30 we're going to increase, and then we're going to start decreasing until we get to 0. So at 30 seconds, I think it looks like about a slope of 1. So I'm going to say here 1 meter per second. Why did I write time here? This is meters per second. At 1 meter per second, at 30 seconds, we're going to have a velocity of 1 meter per second. So this is going to start increasing here. And then it starts to decrease. Let me draw that a little better. It's going to start to decrease down until we have to hit 0 here. Now after that, until about 45 seconds, let's say 45 and 50, it's going to decrease all the way down here until we hit about 45 seconds. And then at that point, it starts to increase, and by that I mean get less negative, because we're going into the negatives now. And at 45 seconds, it starts to get less and less negative until we get to 50. Because if you know more about calculus, I'll go a little deeper into that. This has to do with the concavity of the graph, and at this point right here, it's switching. Also at this this point and this point. That's why I ended up picking 20, 30, 40, 45 seconds, is because that's where the concavity of the graph is changing, and we can figure out the velocity from that. But if you're not too comfortable with thinking about derivatives and calculus, then we can just look at how the position is changing. And important things to know are when the position is linear, position versus time is linear, our velocity is constant. And when it looks like the position versus time, let me get rid of some of these lines here. When it looks like the position versus time is flattening out, so like right here, that's where our velocity is 0. So I plotted those 2 points. This is where the velocity is 0. And for this section here, the velocity is constant. In between those two, we just have to fill in. So this point is where the velocity is, or the position versus time is the steepest. So that's the greatest velocity. And then you just have to plot a few more points and then connect the dots. And that's the intuitive way of how to turn position versus time into velocity. And if you took the derivative of the position versus time graph at every point and ended up just mapping it onto this graph, you get something that looks pretty similar.